welcome. This is the first in a two-part series kind of going over the work we've been doing in the interpreting across time channel. There are a bunch of different projects with various extents to which they're connected between each other, and we've kind of been working on them largely in parallel and largely independently. But recently we've been getting a lot more traffic and attention from people who haven't been working on projects and who have been stopping by and saying, hey, I'd like to get involved. Is there something that I can work on? We've also, for some of the projects, reached points where it's easier to hand things off to more people to work in parallel. And so I thought it would be a good idea to kind of give a briefing on what is happening, what people are up to, what their plans are, and where they're going. So big picture, there are two lines of research that we are focused on right now. Both of them are ultimately about mechanistic interpreting. And what I mean by mechanistic interpretability is understanding the pieces of the algorithms and kind of how they work and explaining why they work. My personal, let's call it philosophy about interpretability research is that the really interesting thing, so the bulk of existing interpretability research focuses on pre-trained models and kind of takes them as given, things that are out there in the world, and now we need to study their properties and understand why they reach the decisions that they do. But I think that's leaving out a really major and really important piece of information, specifically the training process, the training data, and how the model came into existence. To me, the thing that's really interesting is not how can I understand the properties that this model happens to have, but what decisions can I make ahead of time to influence the properties of a model, to cause it to have particular behaviors, cause it to not have particular behaviors. And so that's why I called the channel interpreting across time here referring to over the course of training, where we want to understand not just kind of what the behaviors of language models are, but how those behaviors change over the course of training. So oftentimes we see that certain properties emerge not immediately, but earlier, and it's interesting and potentially useful to know where in training and how much training things happen and particular properties emerge. And of course, because we're mostly talking about transformer models, there's also an implicit scale component here. The general world mindset that I have when talking about these things is that the thing that's most likely to be interesting is identifying the emergence of behavioral patterns over the course of training, and then looking for a fixed model, and then looking at how those patterns change as the model scales, and what stays the same and what doesn't stay the same as the model scales larger and larger. So I'm going to be talking mostly about the Pythia project, as well as work on memorization in language models. These are both primarily focused on a suite of models I'll be talking about in a moment. Nora is later today going to be talking about stuff related to the logit lens. We have a follow-up methodology or an improvement upon that methodology called the focus lens, as well, which is a technique for kind of understanding what happens in early layers of the neural network and kind of identifying if there are decisions that are being made early on, or if particular property, understanding where in the network particular properties occur. So there's a whole bunch of different applications that can be applied to. At ICLR, it was really greatly timed. At ICLR, there were several papers about using the logit lens to do things, and we're like, well, we have a better methodology, so we can just replicate those using a better methodology and wrap that up as like, here are ready-made experiments that people have told us are interesting that we can use to demo why our thing is cool. So that's what she's going to be talking about in, I want to say 5 hours, but as we all know, I have severely fucked up time zones multiple times in the past 36 hours, so trust the most recent timestamps are definitely correct. I think it's in 5 hours. So without further ado, I'm going to talk a bit about Pythia. So no, I need to share my screen for you to see my screen. Okay, and y'all can still see my screen? You see a paper called Pythia?
Yeah.
Great. So let me actually open language So a lot of these large language model papers, so this is the GTP3 paper, for example, have these tables in them where they train models of a variety of different sizes. And they obviously study how models scale. And although increasingly recently there have been papers that have been releasing suites of models that are kind of this like consistently trained, like not all of the hyperparameters are the same because you have to train models of different sizes slightly differently, but at least consistently trained using the same philosophy or equations to derive the relevant parameters. Recently we've started seeing people releasing suites like this. So in December of last year, which isn't so recently, I guess, Facebook released a suite that went up to 13 billion parameters. Then in May, Facebook released another suite, OPT, that went up to 175 billion parameters. The Bloom models are multilingual models that go up to 176 billion parameters that were recently released. And so kind of making these model suites is increasingly, and actually releasing them is increasingly popular. But one thing that is kind of lagging behind that is model suites with intermediate checkpoints. If we want to study how properties emerge over the course of training, and oftentimes it's worth noting that the ending point for these model trainings is pretty arbitrary. So the particular properties a model has when training ends, if that's not stable, if we had stopped 10% earlier or 10% later, and those properties change, that's really important to know, because these models are typically, the forces that cause you to stop training them are financial. You run out of approval to use a lot of GPUs, or simply time. So like for the GTP NeoX model, we wanted to have a model that we were releasing to the public in February, so we had to stop in January so we could evaluate it, write a paper, et cetera, et cetera, et cetera. So those factors obviously have nothing to do with the actual contents of the model itself, and heavily influence how many steps they're trained for, how many tokens they're trained for. So what we've set out to do is train a model suite, broadly speaking, similar to what you're seeing in front of you right now, to the GTP3 suite, except instead of only releasing the models, we would also release intermediate train checkpoints. And we would release a lot of them. So we have 195 intermediate train checkpoints for a wide variety of models. So we have for each model size, we actually have two models that we have trained. We have trained a model for exactly one epoch on the pile. And there is so one epoch on the pile, by the way, is 300 billion tokens. That's the same training length as the GTP3 models were trained for, and is kind of a standard training length to use. But recently, so in the pile, a lot of the data is deliberately upsampled. About 30% of the data is replicated, because at the time we were doing it, that was what was considered the right way to do things. Now, philosophies have changed a bunch, and there is increasingly evidence that deduplicating data is important. That you have sequences that are repeated in many different documents, and that you don't want to train on those sequences many times, especially because they're much more likely to be uninteresting, whether that's because they're just like spam symbols, or like HTML filler, or very commonly quoted passages that just say the same thing. Pieces of famous speeches, for example. So we don't want to train on those with as high of a weighting. So in addition to training on the pile, we also took the pile and deduplicated it and trained on that. Now, deduplicating it made it shorter, so we trained for about 1.4 epochs. I have to do some math and figure out the exact number, but we trained the model on the deduplicated pile for more than 1 epoch, but less than 2 epochs, and for the same total number of tokens. And kind of the magic interesting thing is that all of these models, despite having different batch sizes and stuff, were trained on the same data in the same order. So we use the set seed in the data loader and data shuffler, and the checkpoints are equally spaced when measured in tokens throughout training. So if you take the seventh checkpoint of the 9 million parameter model and the seventh checkpoint of the 6.7 billion parameter model, they have seen the exact same data in the exact same order. And the next data point that they are going to see over the course of training is also the same. And so this is a really powerful way to enable us to explore kind of how training data matters, and what training data affects in the in the model behavior. It is not a perfect one-to-one map between the regular models and the deduplicated models, because the deduplicated models have had a bunch of the sequences removed. But each of the deduplicated models have the same property, where the 19 million parameter deduplicated model and the 6.7 billion parameter deduplicated model have seen the same data and have seen it in the same order. So one of the big blockers for the interpreting across time channel has been, like, I wanted to train these model suites. I envisioned doing all of this phenomenal, this interesting to me analysis on it. Training like 13 billion parameter models is very expensive and very time consuming. Fortunately, as many of you probably know by now, Luthor has come into some very generous donors, and we now have a lot of compute. So we have finally finished training almost all of these models. I caught a couple errors, so there are a couple that need to be redone, but almost all of these models have actually been trained. And so they vary across, 4 orders of magnitude of scale, and we have, like I said, 195 checkpoints. And they're actually, the ones that are finished are on Hugging Face already. So you can check out, here's the 13 billion parameter Pythia model. Here's the 800 million parameter Pythia model. These are just the final checkpoints, because Hugging Face doesn't like it when we upload terabytes of data into a single repository. And large model checkpoints are very large, and 100 of them take up a lot of space. But we're going to be hosting them on the Eye. I've been talking with the archivist, the guy who runs the Eye, about kind of how to do that in a way that is not ludicrously expensive, because most people are, practically speaking, not going to be using all of the checkpoints, even when they do kind of do across-time analysis. But we have those on an internal server, and if people want them, we can give you access to them. And we are going to release it as soon as we have all of kind of the serving details worked out. Haley, there are a couple models that are marked as private. Those are the ones that were incorrectly trained. Is that correct? They need to be rerun?
Yeah, there are a couple of these that are private, and some of them are finished and just need to be re-uploaded. Some of them are work in progress, retraining.
Okay. So this one was trained with the wrong seed. This one...
Those are like secondary models that aren't part of the main suite, but...
So they were just trained with a different seed.
This was one that Shiv trained with seed 42, 6.7 billion, and we can make this one public if you'd like.
When you say seed, are you talking about the data loader seed or the seed as a whole?
Definitely data. We're not sure about the model initialization. I think we would have to look a bit closer, because I had noticed in the logs that he ran. I'm not sure that changing the seed, that's the model seed or not, basically.
Okay.
Like interdependent.
If the code base works the way I think it does, it probably should matter, unfortunately, because it's not like there are several different PyTorch seeds. When you set the seed in the data loader, what happens is that the data loader says, okay, it's time to set the seeds to this number. And then we're going to load the data, and then later the model gets initialized. So unless the data was like separately pre-processed, which I don't think it was, then the models would have been initialized with different seeds, which is, honestly, like, not even a bad thing. Perhaps in some kind of world it would be ideal if only the data shuffle order was different. But I think, here are a couple copies of the models with trained with different seeds is also a perfectly reasonable thing to do. So we have the 6.7 and the 2.7.
The 2.7 is incorrect. That's the one with the wrong data split.
Oh, okay. So it's really the 6.7 that we have right now. Cool. Yeah, so we have a lot of these models. Many of them are correctly trained in public. Some of these have been downloaded like 100, 500 times. That is good to
I
know.
didn't even post about it.
Nothing we do is ever private. Nothing we do is ever private is kind of the upshot. So this is a somewhat old but summary paper. So the idea that I had was that I was interested in writing a paper presenting this model suite as a framework for and kind of presenting an argument where to say that this is the way that you should be studying interpretability, like something that's really important that people are not spending enough time looking at is this idea of looking at training evolution across training and how training varies across scales. And that like the major contribution of this paper would be the introduction of a suite that actually let you did that because nobody else was releasing the right kinds of models. This is kind of old, but is broadly speaking correct. There is not actually any. Okay, never mind. And so it would present the models, present the suite, and also present a couple different analyses, kind of demonstrating the kinds of analysis that this enables you to do. And this would be a mix of taking existing papers and redoing them, but with the added the added abilities and additional analysis, and showing how had they written their paper on our model suite, they could have discovered these other interesting things. And part of it doing new kinds of analysis that were not previously possible. So so far the headline result is we've discovered that training order and memorization are uncorrelated with each other. Data encountered early in training and data encountered later in training are just as likely to get memorized as all else equal, which is to me at least, very counterintuitive thing. That was not kind of just how my mental model of memorization worked. But one about memorization, Haley is currently doing some analysis about mapping bias in training data to bias in model performance. And we've also been talking about doing some work with BLIMP. I know someone had mentioned being experienced with working on grammar learning trajectories and the BLIMP benchmark of linguistic minimal pairs data set. There's definitely some quality issues with that, but it is, as far as I know, kind of the best thing for doing that. And then the second line of work that I wanted to so this is close to being done, and in terms of what can be if people find this kind of analysis interesting and what they can do with it, probably the best thing to start doing at this point is follow-up work. So we have almost all of the models trained and released. We have the final models being trained. If there is some kind of question or like research question that you think would be interesting, either something that nobody's ever looked at before or something that kind of someone has looked at but you think looking at it over the course of training or over the course of scaling would be interesting, sitting down and starting to do that analysis is, I think, probably the best way to build on this work. So to grab one example, the name of that paper is Effect of Pre-training Frequencies on Few-Shot Reasoning. There's a really interesting paper by Samir Singh and some people at the Allen Institute for Artificial Intelligence. And what they were looking at is how pre-training frequencies affect the model's ability to do arithmetic. And they this is their main plot. And what you see on the x-axis here is the frequency with which particular arithmetic expressions show up in the training data. And the y-axis is the model's performance, and this is on GTBJ 6b. This is apparently 2-shot. I thought it was 0-shot for some reason. I think this is really interesting, but one really big limitation of this paper is it's entirely correlational. They took a pre-trained language model and said, all right, we're going to do this. Redoing this in a causal fashion, where you can actually kind of, we do have the ability to modify the training data to train the models for a little bit extra, for example, on a certain subset of arithmetic expressions is one example of the kind of analysis that we can do that I think would be really interesting. Yeah, but there's definitely a lot of things along these lines. Whoops. And the other thing is, so I had mentioned how training order doesn't influence memorization. We've actually been discovering a lot of interesting patterns in memorization, and to the point where that's going to be spun off as its own paper. So one of the results is going to be put in the Pythia paper, but there's actually a lot of really interesting patterns that we found in our memorization exploration, and so we're going to write a paper exclusively about that. So to give a quick overview of some of that. Let's see. These are all 13 billion parameter models. So what you're looking at here is a notion of memorization. I'm going to skip over what that notion is for a moment, but we're measuring the extent to which pre-training data points are memorized by the model. And we on the x-axis here we have the sequence index, so where it was located in training, and on the y-axis we have the accuracy, the measure of the extent to which the model was memorized. The model memorized the data. And each of these curves, each of these lines are lines of best fit for the points, and each color represents a different checkpoint. So these are all 13 billion parameter models. The pink one has been trained the least, and the red one has been trained the most. So we do see a pretty severe slant here, but over the course of our analysis, what we've discovered is that the reason for this is that models that have been trained more are just better at generating realistic text. They are actually better fit to the distribution as a whole, and that does not necessarily means that they're better at memorizing things. So one way we can see that is if we go from, so typically instead of talking about, a memorization score for all data, people talk about the most memorized points, the points that are quote unquote actually memorized. So if we go look at the 10% most memorized data, the lines flatten out a lot. Also notice how the scores go up massively. Here they're at like 10%, here they're at like 50%. And then if we go to the 1% most memorized data, you can't see most of the curves because they're all straight lines at 1. So the top 1% most memorized data for the 13 billion parameter model at most stages throughout training has 100% memorized 1% of its training sequences. The plot I am currently looking for is not actually, oh, here they are, great. So another way you can kind of visualize this is through, what order are these in? 2, 4, 6, 8, 10, 12, 14, there we go. So I'm going to stick with the 13 billion parameter model because the largest models memorize more, and that's kind of easier to see in the graphs. We can see some of these effects at smaller scales as well. So what you're looking at here is kind of a plot of, in the middle, is a plot of the memorization accuracy. Whoops. The memorization accuracy for all of the points. The higher the point up is, the more memorized it is. The lower down it is, the less memorized it is. And this is actually a heat map. So there are a billion-ish points on this map. Sorry, 100 million-ish points on this graph. Obviously, like your puny human eyes can't make those out, so it's a heat map. The purple is the least density, and the yellow is the highest density. So these are really high density points at like 0. But there's a very useful summary technique where we're summing across the rows. So basically we bin this into, I think, 50 buckets, and this is a histogram where we show the frequency of the points that have have like a score of 0, a score of, I think it's 0.02, 0.03, etc., all the way up to 1. And what you see is this really nice exponential decay, and then there's a big spike at 1. And you can sort of see that visually, that there are a lot more points along the line at 1 than there are along any horizontal line really between 1 and, say, 50. The other thing that's actually really interesting from this scatter plot is you can see visually just how few points have a high memorization score. So, the number of points that are above 0.4 and below 1 is like maybe 100 or 200. But like I said, there are hundreds of millions of points on this graph. That's basically a frequency of 0. So there's this large intermediate band where the memorization accuracy is basically, where there are basically no points that fall into that bucket, but the perfect memorization bucket does have a lot more points in it, and then the very poor memorization bucket also has plenty of points in it. And we have these kinds of graphs at different scales. So this is the 2.7 billion parameter model. You see the same sort of pattern. The primary difference between these, it auto scales so you can't tell, but the primary difference between these is the sharpness of the decline. We even have these for smaller models. Here you can see that not very many points got fully memorized, and so it's largely blank up here. And then the last thing I wanted to show you is correlation. So one of the questions you can ask once you start doing this is, how does the memorization of a data point by a particular model correlate with the memorization of the same data point by a different model? So there's a couple mistakes in here because, as I mentioned, we discovered that some of the models were mistrained. But most of this is correct. And this is a heat map of specifically the correlation. So you get points for, so if you look at the sequences that are memorized by the 800 million parameter model, and correlate that with the sequences that are memorized by the 350 million parameter model, the coefficient of correlation is 0.4. And you see this really interesting block structure where for the small models, they kind of all highly correlate with each other. But then once you go from 350 million to 800 million, there's actually a very steep drop off. And then the 800 million models, so the 800 million models are both bugged. So I don't know exactly kind of what this is going to look like. But then you see this increasing block structure going up the lines. So the 13 and 6.7 billion parameter models are very similar to each other, but very different from the 2.7 billion parameter models. And I think this kind of analysis is really interesting, and I can't wait until we have kind of all of the models trained so we can do really detailed analysis of this. One thing that's really notable, I think, is that a lot of these numbers are zero. There is no correlation between the data points a 13 billion parameter model memorizes and the data points that a 19 million parameter model memorizes. And so this can be viewed kind of as a strict limit on the extent to which you can use kind of the scaling laws perspective, which says, oh, you can just study small models and extrapolate the results to big models. In this particular case, that's not, if what you care about is which data points are memorized, which is something people care about in a lot of contexts because different points, because it's worse if some data points are memorized comparatively to others. It's worse if a text model regurgitates a passage from a copyrighted book. It's worse if a model like DALL-E 2 or Stable Diffusion has Mickey Mouse's face memorized and can reproduce that really easily, comparatively to things that are not copyrighted or are not owned by highly litigious companies. And so we do actually care which individual data points are memorized because they're not interchangeable. And so the fact that you can't extrapolate from what small model is memorized to what large model is memorized is really interesting and potentially impactful. Yeah, that is kind of the stuff I have to present on. We have like 15, 20-ish minutes, and I was hoping to kind of chat, answer any questions you guys have about the work we've been doing already, and how you can get involved with at least this line of research. And one, I guess before that, the most immediate to-do items for the memorization paper are, we have some statistical analyses we need to do. And neither Yusai nor myself are particularly adept at advanced statistics. So if you are not shy and if you are not afraid of statistical testing with cross correlations, or doing event arrival models or survival models, one thing I want to do is look at over the course of training and use a survival model to tell me if model data points that are memorized early in training stay memorized throughout training or whether they tend to disappear. So if that sounds like that's kind of like statistically up your alley, I would love for you to tell me that so I can set you up to do some of the last analysis we need to do. Yeah, that is my presentation. So questions, comments, people want to get involved?
Hey, thanks for putting this on, Stella. And FYI, I'm a little sick. I'll probably not be as coherent as I otherwise could be. But one of the projects that Haley had suggested I look at, and that Igor has gotten a jump on, is this blimp work. Mm-hmm. Is that something that is like still one of our priority research work streams? I think also another, at least like for my interest of getting involved, is this would be my first time doing like any AI research. So if this is like a very vital part of our work stream or something that like maybe has enough ambiguity that it's not like a great starter research direction, it might be better if I contributed elsewhere.
So I know I made a face when you said that. The blimp analysis is probably going to be somewhat core to the paper. I am personally somewhat skeptical that we are going to get very compelling results. The more I have looked into blimp, the less I have been impressed with their analytic design and the quality of the questions in them. There is a large number of questions, for example, for which a bigram model or a majority vote model scores quite highly. So some of them have heavy class imbalance. Some of them have like the first couple words tells you what the answer is going to be, and they don't have although they do document a wide variety of linguistic phenomena, they don't test you on very diverse examples of that linguistic phenomena. And so I'm worried that the ultimate results are not going to be as meaningful as we might hope. To kind of improve on that, there's someone that I've been chatting with over email who is kind of looking at filtering the blimp models. The blimp evaluation tasks. So there's a lot of them. There's 57, I think, 57 evaluation tasks. And so someone is kind of working on filtering them and identifying which ones might be more interesting and more meaningful to score highly on. Because of kind of that worry about the interpretability and the contentfulness of the results, I might not identify that as the most tractable starting point, although technologically it is very straightforward. We have a code base that we've implemented that we can use to evaluate a wide variety of models, and it has blimp, and it also has a lot of others. And so perhaps, I don't know if we've actually, Haley, have you finished the evaluations of the models on like standard NLP benchmarks, or is that something that you could use a hand with?
If someone is able to get access to the cluster and we have someone sort of running those evaluations with the harness, that would definitely be helpful.
Yeah, so that actually might be the most newbie-friendly thing for a couple of reasons. One is that it's honestly, like as you were saying, kind of hard to fuck up. And two, it involves actually getting some meaningful knowledge about our infrastructure and how to use it that will be like helpful for getting more involved in future projects. So the model checkpoints right now are on a private cluster. So we'll get you login we get you login credentials, teach you how to use it, and kind of show you how to run evaluations of models on there. But the evaluation code base is pretty straightforward. We've put many hours into building it and getting it to work up.
Sure. Sounds like a great place for me to start. Thanks. I'll be so Haley, I'll reach out to you and maybe get that rolling.
So if these are evals for the, I guess, Pythia checkpoints, the 6.7 and 13, I did generate those results. I think I shared those on the Discord at some point.
Yes.
Happy to also help Kyle if you're looking at some of the other models.
Yeah, sure. Thank you.
Yeah. I know that you did post those. I guess if I can, do you have the raw data? Like you posted graphs, but do you have like the tables of raw data?
I have it. No, so I have the original JSON files. I also have it in NumPy formats. I have the graphs. I have it in Jupyter Notebook. So whatever's the most convenient way.
Perfect.
I'm happy to.
Honestly, we don't have a particularly good methodology for taking the output of the evaluation harness and like visualizing it and plotting it. If you do, that would be A+. What I use mostly is something that John and I whipped together while we were writing the G2B NeoX paper, and I was literally editing the notebook on the fly, modifying it to work with different kind of evaluations and kind of different sorts of analyses I wanted to do. So if you have something that's relatively stable, that would be very useful, and honestly would be a useful thing to contribute to the evaluation harness as a visualization notebook, even just like demonstrations on how to visualize models results after you've run them. That would be really useful. And yeah, we will. So you have the 13 and the 6.7 billion parameter, but not the deduplicated ones, right?
At least one of them I did the deduplicated one. I think the 6.7 billion, the deduplicated one, was available. I didn't know if is the 13 billion deduplicated one, is that one finished training?
I think so. Let's go find out.
Should be. Yeah, I can confirm. The 13B dedupe is the name on S3.
Okay, so it's not on Hugging
Okay.
Face yet, but it is on the S3 drive.
Okay. On the S3. Yeah. So I can get it from S3. If that one hasn't been run, it's pretty straightforward for me to run it. And then I do have some tools around kind of doing the visualization, basically going from the JSON files to pandas and then to plot, so I can see if I can share that in a way that will be helpful to others as well.
Yeah, and I would love to take a look at that and kind of brainstorm kind of how we can make that most widely useful.
Sure. And Kyle, I'm happy to show you where what I have and where that is and where where it might make sense for you to plug in if that's of interest.
Yeah, thanks for the lead.
Any other thoughts, observations? Oh, you should do X, you shouldn't do X, even if you don't want to be the person doing it yourself.
One random question that sort of popped in my mind, Stella, as you were talking through Pythia. One aspect of training that I feel like is underexplored, or maybe just something that I'm not caught up on the research, is to what extent, like, if you train at let's say cosine decay for 100,000 steps versus had you trained for 50,000 steps, how would the capabilities develop over checkpoints? Have you given that, like, do you have any opinions on that, or have you given any thought of that as to a potential interesting angle?
So there is some work on that. The paper Scaling Laws for Neural Language Models has an ablation on that, as well as the paper, whatever they called, Training Compute Optimal. Oh, I stopped sharing my screen. Let me go back to sharing my screen. Nope.
I mean, I recall it was kind of a big deal for the Chinchilla paper, which may be one of the ones that you're...
Yeah, so the Chinchilla paper, yeah, so this is the Chinchilla paper, and this is the Scaling Laws paper, and you were asking about learning rate. Yeah, so they steps, PF days, compute budget. Where are the learning rate curves? Here we go. No, these are not the learning rate curves. Why does the word learning rate? Oh, it's beneath. So the Scaling Laws paper did do some ablations along things like that, with the learning rate, with the optimal model shape, kind of the height, the width to depth ratio, for example. Notably, and this is something that people widely forget, this paper actually came out before GTB3 did. They did this work first. Nobody read it until after GTB3, but they did this work first. So the numbers from the GTB3 paper are actually, at least as far as OpenAI's experiments were concerned, at the time, optimally designed. And so most people who use cosine decay, generally speaking, kind of copy their numbers, and that's part of why people are specifically sticking to their model sizes. Another is for comparability, but one of the main reasons is that way you don't have to go figure out all the other hyperparameters yourself. I don't think that there's anything in the Chinchilla paper that says that you shouldn't trust their analyses of learning rate.
Yeah, I think that the difference in one of the differences in the analysis, as I understand it, was if you train a model for 200,000 steps and then you look at how it behaved after 100,000 iterations, it's going to perform differently compared to if you train the model for 400,000 iterations, just because of the different learning curve shape.
Yeah.
That's sort of in some sense, to me, kind of relates a little bit to the idea of like how do models learn over time, and how it relates to the schedules. I guess that's why I thought it might be potentially
Yeah, no,
overlooked.
I mean, I think that makes a lot of sense. And learning rate is also closely connected to batch size. They have some interesting comments about batch size, and we've actually been experimenting with batch size. So if we go to the table over here, some of our batch sizes are very large. So we trained the 19 million parameter model with a 2 million batch size. That is much, much larger than anything GTP3 would have done. So GTP3 used, I don't have it open anymore. So GTP3 used a 0.5 million batch size up until they reached a billion parameters, and then they went to 1 million, and then for 6.7 they did 2, and for 13 they did 2, and then they went to 3.2. So when we go and use a batch size of 2 million for even like a 19 million parameter model, that is like an order of magnitude plus bigger than the batch sizes being used in this paper, which I suppose does indirectly impact learning rate. We did not specifically do any study to assess what is optimal. Honestly, the biggest reason for that is that we are still implementing the MUP, the maximum update parameterization, in the GTP NeoX library, and I kind of want to have that because to help with those experiments. But doing that kind of ablation is something that is on my radar and is something I'd love to do. But ultimately, like at the end of the day, the primary goal of the Pythia models is not to have the best performance for their size. Like there's 1,000 papers whose goal is to have the best performance for their size, and that was not very high on our list of desiderata. We're much more, the goal with these particular models was much more focused on interpretability and kind of making it a consistent platform that people can use to do research, rather than squeezing out the most performance in each model we could.
Cool, thank you.
All right, so I do have a question, which is, do you have any thoughts on projects that might be sort of somewhat internship-led in this, within Pythia analysis? So maybe the survival model thing with regard to memorization, if it was connected to other things, because I do have, as I discussed in the private channel, now a bunch of people who are sort of interested in working on this kind of thing.
I may have missed that. You have a bunch of people who are interested in working on this. Where did you discuss that?
In research leads.
Oh, yes. I'm sorry. I am tired. Yes, we do. So I am working on figuring out what our compute budget is going to be for the coming months. But I think that there's a good chance that in addition to being able to have people do some kind of compute intensive work, we're going to have the ability to retrain several of these models. And so some kinds of analysis are intensive because you need to train models on slightly different data sets. So for example, if they want to take the pile and remove all of the addition equations that contain the numbers 17, 87, and 32, and retrain all of the models just without those specific additions and kind of look at how that affects arithmetic generalization. I think that's a potentially really high impact thing that we can study, and it's relatively straightforward to, at this point, spin up and run models at a wide variety of sizes. The bulk of the work is going to go into carefully designing the experiments to get the most out of each run. So whether, and so part of that is like figuring out what kinds of conclusions we want to be able to potentially reach, as well as making sure to structure kind of the data interventions in a way that allows us to draw causal conclusions.
All right, great. Yeah, that sounds very interesting. I think that would be kind of perfect for what I'm thinking of. So I will message you about this and we can sort of discuss it.
Awesome. Yeah, and what he was talking about there was that we are going to be getting some interns in January. Is that the right month?
Well, these people specifically are looking to start in December.
Okay, great. Yeah, we're going to be getting a small group of interns who are specifically interested in interpretability and alignment in December. And they're going to be with us for a couple of months and are looking for interesting projects along those lines to contribute to. They're from, where are they from again?
Mostly Cambridge University, some other universities around the UK and Europe. We've had a good spread of applications so far. We have like 10 applications, but maybe there's kind of a mix of like really good undergrads and some PhD students. So.
Okay. Yeah, so I guess in closing, so I am leading most of the work that I am talking about right now, that I've talked about today. Like I said, Nora is going to be talking about the work with stuff like the logit lens and with model probing more generally. There's a lot of different probing stuff that's been going on that is pretty exciting, and I'm excited to hear about what they've been up to because I haven't been keeping in touch as much as I should. Haley is a really good point of contact because she has also been heavily involved in this and is less busy than I am. And she's probably a better person to reach out to in terms of getting access to the models or getting immediate responses. But I'm definitely available to discuss kind of scientific priorities and how we are trying to go about doing this analysis. All right. Thank you for your time. I hope this was interesting and that we'll be able to collaborate in the future.
Thank you. Have a good rest of your day.
Bye.